Welcome back to our chemistry flipped classroom. And we're continuing our discussion of thermochemistry. So we've talked about specific heat and how we use that to measure the amount of heat transferred in a process. So today we're going to jump in and we're going to learn about this concept called enthalpy, which is really just the heat transferred in a chemical reaction. We're going to talk about several different forms of enthalpy. Enthalpy of reaction, enthalpy of formation, enthalpy of combustion, and even a few others. And we're going to learn how to solve problems that involve those enthalpies and how to use something called Hess's law. So before we can do that, let's jump in and talk about enthalpy. So enthalpy and heat are nearly interchangeable quantities. Enthalpy cannot be directly measured. What can be measured is a change in enthalpy. If a system is kept at constant pressure, the only work that can happen is expansion work. So the amount of energy absorbed or released by a system is the enthalpy change. So an easier way to think of that is to say that enthalpy is the heat given off or absorbed by a chemical reaction. Enthalpy is a state function. So our change in enthalpy, like any other change in energy, is a state function. It depends on the initial state and the final state, but it doesn't depend on the path we take to get there. So it's a state function. And that's going to become important when we start talking about Hess's law. So if enthalpy can't be measured directly, how do we measure it? So we usually use a process called calorimetry. So calorimetry comes from that same root word as calorie, heat. And we measure the amount of heat that is absorbed or released during a physical or a chemical change. And most of the time when we do calorimetry, we're measuring the change in temperature of a known quantity of water in something called a calorimeter. So this drawing shows us what we call a bomb calorimeter. It keeps things at a constant pressure. It's called a bomb calorimeter, not because it's going to explode, but because there's a container inside called a bomb. And that is inside an insulated container. There's water all around that steel bomb, and we measure the change in temperature of the water. Obviously, in most high school and even a lot of college labs, you're not going to be working with bomb calorimeters. More often, we work with what we call a coffee cup calorimeter. So we're using nested coffee cups to measure the change in temperature of water, again, to see how the temperature changes, and use our Q equals mCp delta T equation to determine how much energy is absorbed or released by that reaction. We use the specific heat of water. We measure the temperature change of the water. The water is the surroundings. By finding the change in heat of the surroundings, we know how much heat was absorbed or released by the reaction. We can measure these reactions, and then we can use pieces of that information to calculate the change in enthalpy of reactions that are not easily done in a calorimeter. So we can directly measure changes in enthalpy using a calorimeter. We can also calculate changes in enthalpy. But in order to do that, we're going to talk about something first called the enthalpy of formation. So when we talk about enthalpy of formation, we are talking about the amount of energy that is released or gained in the formation of a product. So enthalpy of formation means when something forms, how much energy is released or gained. Now, when we talk about standard enthalpy of formation, we are talking about the energy that is released or gained in the formation of 1 mole of a substance, and only 1 mole of a substance, from its component elements. We can form things in lots of different ways. We know there are a lot of different synthesis reactions, But if we make something simply from its component elements, not from two other compounds, but simply from its component elements, and we form exactly 1 mole of it, then that is the standard enthalpy of formation. So this means that these have been measured over and over and over again. There are tables of enthalpies of formation of thousands of compounds. And so we'll use those when we get to our applications in Hess's law. We can also learn something about our compounds just by looking at their enthalpies of formation. So the enthalpy of formation of any element is always, in its standard form, is always going to be 0, because the formation of an element from its component elements isn't going to absorb or release any energy. So standard enthalpy of formation of any element in its pure state is 0. If we have a product that is formed by an exothermic process, meaning that it started, its elements had more potential energy than the product does, those products are extremely stable. They're going to have negative enthalpies of formation, meaning that energy was released as they were formed, and they're very stable. Products that are formed by endothermic processes are not stable. So if it requires energy to make a product, it's not going to be very stable. So that we can think of this kind of like if we have a pen and we drop it and it's on the floor, it's released energy, potential energy, changed it to kinetic energy, and then eventually to heat energy, and it's in a more stable location. But if we take that same pen and we balance it on the edge of the desk, it's now less stable. And so we've put it in a higher potential energy state. So the lower the potential energy, the more stable the product is. Okay, so let's talk about Hess's law. So because enthalpy is a state function, Hess's law says in going from a particular set of reactants to a particular set of products, the change in enthalpy is the same whether the reaction takes place in one step or a series of steps. So if we go back to our analogy when we talked about state functions, and we know that the path a hiker takes to the top of the mountain doesn't affect the amount of gravitational potential energy the hiker has at the top of the mountain. That in the same way, the path of the reaction does not affect the change in enthalpy. So the energy difference between reactants and products is independent of the path taken to get from one to the other. So that means that mathematically, we can find the enthalpy change of a reaction, so the delta H of a reaction, by adding up all of the enthalpies of formation of the products and then subtracting all of the enthalpies of formation of the reactants. So what we're really doing is we're saying, okay, here's the potential energy of the products minus the potential energy of the reactants, and that gives us the potential energy of the reaction. But since what we're talking about is the energy released in the reaction, we're talking about enthalpy. So the enthalpies of formation of the products minus the enthalpies of formation of the reactants gives us the enthalpy of the reaction. This is what we just went through. Remember, there's tables of heats of formation. So this application of Hess's law is going to involve looking up those values. And the enthalpy of formation of any element in its stable form is always 0. So let's look at an example problem. In this problem, we're being asked to calculate the enthalpy, the change in enthalpy for the combustion of methane. So this is enthalpy of reaction. It's also enthalpy of combustion because we are combusting 1 mole of methane. So we're going to use that equation. The enthalpy of the reaction is equal to the sum of the enthalpies of formation of the products minus the sum of the enthalpies of formation of the reactants. And we're going to go look these up in our table, and we're going to find that the enthalpy of formation of methane is negative 74.80 kilojoules. The enthalpy of formation of oxygen is 0 because it's an element in its stable form. of carbon dioxide is negative 393.50, and of water is negative 285.83. So we're going to add up the enthalpies of formation of the products. So that's going to be carbon dioxide plus 2 times the enthalpy of formation of water. And we're going to subtract the enthalpies of formation of the reactants. So that's going to be this methane plus 0 for the oxygen. So we get the enthalpy of reaction here, and that is negative 890.36 kilojoules. Because this is addition and subtraction, we're going to the last common decimal place. So our answer is going to have 5 significant figures. So that's one application of Hess's law. Enthalpy of formation of the reaction is equal to the sum of the enthalpies of formation of products minus the sum of the enthalpies of formation of the reactants. Now there's another way to look at this. The enthalpy of reaction can be determined from the sum of multiple reactions that add up to our target reaction. So this way of looking at it is kind of like looking at a puzzle. This is where our information from our calorimeter is going to come in. So if we want to know the enthalpy of a reaction and we don't know the enthalpies of formation, they're not in the tables of all of the products and reactants, then we're going to be using known heats of reaction from calorimetry data to determine the enthalpy of our target reaction. So let's take a look. Here's our example. We're looking again at the same problem, calculating the enthalpy of reaction for the combustion of methane. But this time, instead of looking up enthalpies of formation, we're given some information, we're given some reactions that can be manipulated so that they will add up to this target reaction. So I'm going to shift us to the other screen. So give me just a second here. Okay, we got to flip that around again. All right, so this is our target reaction. This is the combustion of methane, and this is what we're trying to get to. And we are given these 3 reactions. And so what we're trying to do is kind of put this puzzle together. And the way that we want to look at this puzzle is we want to look at trying to get to this reaction. So the first reaction that I'm given, I have carbon plus 2 hydrogen yields methane. Well, I have methane in my target reaction, but it's a reactant, not a product. So I know that I need to flip this equation around. And right now, this is written as an exothermic reaction. The formation of methane is exothermic. But if I flip this equation around, the delta H gets the opposite sign. So I'm going to take this reaction and I'm going to flip it. So instead of having C plus 2H2, I have CH4 forming carbon and hydrogen. And now the delta H for that is a positive 74.80 kilojoules. And I'm just going to draw a line through this one so I don't confuse myself with that one. Okay, so now I've got methane as a reactant where it needs to be. Okay. And I look at my next reaction and I can see that I have carbon and oxygen forming carbon dioxide. And I see that I have carbon dioxide here as a product, and here it's a product. And I have 1 carbon dioxide and 1 carbon dioxide. So that looks like that's probably in a pretty good place. And I can see that I'm going to have carbon, that's going to cancel out. So I'm going to leave this one alone for right now. Now I take a look at this one and I see that I have water as a product, but I only have 1 water molecule and I need 2. So I'm going to multiply this whole reaction by 2. And I'm going to have 2 hydrogen plus 2 times a half is 1. So oxygen forms 2 waters. And because I'm multiplying the whole reaction by 2, I'm also going to multiply the delta H by 2. So this is going to become negative 571.66 kilojoules. And once again, I'm just going to draw a line through this. Now, if I add all these reactions up, these three reactions, this one, and this one, and this one, I will now have methane plus oxygen plus hydrogen, 2 hydrogen, plus oxygen yields carbon. Oops, I left out a carbon when I brought it down, so I'm just going to put it over here. Plus 2 hydrogen plus carbon dioxide plus 2 waters. And now we can see that I have carbon here and I have carbon here, so I can cross those two out. And I have 2 hydrogens here and 2 hydrogens here, so I can cross those out. I'm just simplifying and combining like terms. This has become an algebra problem now. Now these 2 oxygens I'm going to combine together. So I have CH4 plus 2O2 yields CO2 plus 2H2O. And I can see that I now have my target reaction just by adding up these 3 equations. That means that I can add up the enthalpies of these 3 equations, and that will be the enthalpy of this reaction. So delta H equals 74.80 plus negative 393.50 plus negative 571.66. And these are all in kilojoules. And when we add all that up, we get, let's see, negative 890.36 kilojoules. So we arrived at the same answer that we got by the other process, which makes sense, but it's a different way of getting to it. There are times when this is the way we have to do it because we don't have enthalpies of formation for some of the reactants. Okay, there's one more application of Hess's law that we are going to jump back to. So let me one more time share the screen here. Okay, so there's our, walk through that whole process. All right, and the last application is that if we know how much energy is released by a reaction, we can use that information to determine how much energy is released for a specific amount of reactant consumed or product made. So this really is just another application of stoichiometry. So in this case, we're being asked to calculate the heat that is released when 8 grams of methane undergo complete combustion. So the first thing we're going to do is we're going to convert the information that's given into moles. So we know that 8 grams of methane, we're going to use molar mass of methane to convert that to moles of methane. Then we also know that the enthalpy of the reaction is negative 890.36 kilojoules. And from our balanced chemical equation, we know that that's for 1 mole of methane. So we're going to put 1 mole of methane on the bottom and negative 890.36 kilojoules on the top. And so when we do all the math and cancel out grams and moles, we get that 444 kilojoules of energy are released when 8 grams of methane are combusted. So we have 3 different applications of Hess's law. One of them really is kind of an application of stoichiometry. All right, so we can write any equation by designating the value of delta H in that equation, and then we call that a thermochemical equation. If it's an endothermic reaction, if we put energy in, the value of delta H appears as a reactant. If it's an exothermic reaction, the value of delta H appears as a product because it gives off that energy. We can also write a thermochemical equation by designating the value of delta H off to the side. When we do that, we use a positive number for endothermic and a negative number for exothermic reactions. Okay, so we've talked all about enthalpy, and enthalpy in its most generic form is the energy given off in a chemical reaction. But we kind of talk about different types of enthalpy. So we started out by talking about enthalpy of formation, that being the energy given off or absorbed when a compound is formed. We can also talk about the enthalpy of combustion. Enthalpy of combustion, kind of like enthalpy of formation, is defined as the energy released in the complete combustion of 1 mole of a reactant. So we have to be careful about how we write those equations to make sure that we're only combusting 1 mole. We can also talk about the enthalpy of solution. This is the energy that is released or absorbed in the dissolution of 1 mole of a substance in 1 liter of water. So this is just dissolving something into water. It's either going to give off or absorb energy, and we call that the enthalpy of solution. The enthalpy of reaction is the energy released in a reaction as represented in that balanced chemical equation. We can also talk about the enthalpy of fusion. So this is the energy released when a mole of a substance freezes, goes from the liquid form to the solid form. We can talk about enthalpy of vaporization, which is the energy that's required to vaporize 1 mole of a substance. So 1 mole of a substance goes from a liquid to a gas. And then, of course, we've already talked about enthalpy of formation. That's it for enthalpy. As always, if you have questions, please let me know. I look forward to seeing you in class.